difficulties when you have everything online. And for your information, the stand of our university, our rectors are saying, there is no way for us to replace our face-to-face teaching. We may blend, but we cannot change everything to online. There is no way, especially in medicine, almost impossible for us to teach you skill, everything through online. Impossible, yeah? Okay, now I'm recording everything. It's okay. We can. I just want to see your face for the time being. For the first part, and then you can disable your video. At least your connection will be better. So once I start my slide, you can off your video. After all, we are not able to see the face after all. So more important is the screen. So I will start now. Okay, I just started the recording. So I will present my. Tell me if you are not able to see the presentation. Can you see the full screen?
Yes.
All right. Bismillahirrahmanirrahim. So today I'm going to bring you to basic statistics. Basically, I believe starting from today, Dr. Adil will try his best to teach you practical biostatistics. So the basic of statistics you have learned in year 1. However, coming next batch, I believe they will be learning everything only in year 4. Year 1 only just mostly lecture, not really any practical session at all. So what we try to learn today, let's see if I can control this. So basically, at the end of the practical session, which is the practical session comprises my talk here, which is the introduction for 1 hour, and ultimately Dr. Adi will bring you to the actual work on statistics. We try to give as best as possible, as best experience. So basically we try to mention the fundamentals of statistics, what I'm trying to give you today. And after this, Dr. Adi will bring you to actual statistics. So the statistics can be divided into 2. One we call descriptive statistics. Number 3 there is analytical statistics. Okay, for you to remember, to understand, when you are analyzing or describing one variable, so we call that descriptive statistics. When you try to analyze or try to look at or try to describe relationship of 2 variables, so we call that analytical statistics. So very easy. When you involve 1 variable, descriptive, more than 1 is analytical statistics. That would be a very general, crude description or tips I would like to give to you. It is not entirely true actually, but for you to understand easier is that when you try to analyze 1 variable, descriptive statistics. When you try to analyze relationship of 2 variables, it becomes analytical statistics. Remember, yeah, relationship is always analytical. Okay. So first, the fundamental, I will be talking about 4 things. And before I end, I will mention to you the snapshot of descriptive and analytical statistics. So fundamental. The fundamental premises I would like to convey here, there are 4. One with regard to what is statistics is all about. And more importantly, when we analyze actually the second part of the analysis, which is the relationship, which is the analytical part, is mainly why people do analysis. And then how we quantify observation, and how about what is distribution of data. So this could be important before you analyze any of your data. Oh, by the way, you can always stop me at any time. Okay, representativeness. Whatever we do in our life is based on our observation. We observe, we believe what we observe. But the problem is that what we observe might not be the truth. So it is very important that when we observe something, our deduction, our interpretation is correct. So those are very important. Okay, now, And one of the most important element of statistics is that when you analyze something, you obtain certain information. You want to know whether that information represents the actual population of interest. You want to study about diabetics, you study diabetics. So whatever outcome from the analysis should represent that diabetics. But you must remember that diabetics is a wide spectrum of condition, from very mild diabetes to very severe comatose situation diabetics. So it is not as straightforward as it is. So we have to substantiate, we have to justify the term that we use. All right. And then I would bring you to a very simple term about representativeness in terms of population. When we observe the sample, when I say the word observe here, I do not only mean looking, observe. In Malay, we call it cerap, cerapan, cerap. So observe is not pemerhatian. You must, I hope you understand that. Observe also means measurement. When you measure something, when you weigh someone, when you measure the circumference, you measure the height, so, or you measure the speed. So those are, we call observation. Observation also, the other word is measurement. So when we observe sample means a portion of a population, we are hoping that that sample will represent population. If I give you this diagram over here, you can see that, let's say, these are people represent those in Peninsular Malaysia. And on the, on the right side is actually the sample, the size of sample that we can afford to sample, meaning to say that our sample size is smaller than actual Malaysia or Peninsular Malaysia size. So we need to, more important is that even if the size is small, we are hoping that this sample here represent the population. So those are very important, whether this sample here represent the entire Peninsular Malaysia. All right. So one of the important characteristics of the sample is that, I just want to mention here is that anything derived from the sample here, any measurement, any calculation we obtain from the sample here, we call a statistics. If we are able to sample everyone in Malaysia, we call this parameter. I hope you understand. The characteristics of the sample we call statistics. The characteristics of the population is called parameter. Okay, so I hope you understand by now that parameter can be something that is hypothetical estimate, because nobody would be able to sample the entire population. Nobody can. So parameter is always an estimate. It's always, only God knows, only Allah knows the actual, let's say if you're talking about, let's say we talk about prevalence of hypertension, for example. We, in Malaysia so far, the latest NHMS, what we obtain is that the value is meant for the sample, but we infer the value to the whole Malaysian. Do we know whether the estimate we obtain from our sample is representative of the population? No. No one knows. Nobody knows, because it is, we only know that if we are able to sample everybody in Malaysia, of which impossible we will do that. Nevertheless, just follow me through first. So statistics trying to estimate parameter well. So the statistics able to estimate parameter very well if the sample that we selected represent population. Okay, again, I go to this slide. If this group of samples, small sample here, really represent Malaysia, so this value here might be able somehow to represent the population. So the key word here is that everybody here in Malaysia here, everybody here must have equal chance to be selected. Everybody here in Malaysia have equal chance to be the sample. So that is very important rule to sample. All right. If, for example, only those in big cities would be sampled, so it becomes biased. Our sample may not be able to represent people in rural area, or our sample only represent those in residences, in houses, So we are not able to represent, let's say, when you are in Mahalah, for example, people don't go and knock your door and survey you because you are in Mahalah, you are in university. Or those in prison, nobody knock the cell and ask them survey. Hypertension, diabetes, no. So meaning to say that, there will be some bias. That's why even NHMS, the best design for the country, not able actually to represent the country 100%. However, what we are doing, what I've been done is the best to our capability. All right. So far, any question? The concept of representativeness. Okay. Now, so how can we measure? Okay. Now the problem is that we said that we want to know how good the statistics is. So to compare whether the statistic is good or not good, we compare to the parameter. The problem is we do not know what is the parameter. We do not know. However, we are able to estimate parameter. How? Okay, I'll give you an example here. Let's say in this sample, we have the green and the blue circle over there. We want to know, and then let's say this is the population. So the parameter of the prevalence of the red circle or the red ball or the red circles there is 51.4%. Let's say 18 over 35. Okay, total population 35. Those with the red circle is 18. So the prevalence is 51.4%. Let's say we get one sample. And this sample, we can afford only to select 6 circles. From the 6 circles, randomly, we managed to get 3 reds. So that gives the prevalence of the red is 50%. So imagine if I can afford only 6, not 35, only 6. Our sample size that I can manage to sample is only 6. So I sample randomly, I got 6 circles, of which 3 are red. The rest are blue. So it give a prevalence of red of 50%. Let's say I put everything back. I do the second sample. Remember, yeah, I put the previous one. No, second sample, still 6. But this time I may get only 2. So it gives a prevalence of 33%. I put everything back. I sample the 3 times, the third time. So I may get more, let's say 4. I got 67%. So in actual reality, when we sample, we don't sample 3 times. We sample only once, right? But I want to give you a simulation. What if I sample 3 different times? This is the possible outcomes. That is also possible that I get all red. There is also a possibility that I get all blue. That's a possibility. But knowing the parameter to be 50%, almost half, or more slightly more than half of the total population. So if we random properly from the 3 experiments here, which one you believe is the most likely outcome? The first one, the second, or the third one? Which one? Guys, which one?
The first one.
First one, right? Because in the population, the parameter is 50%. So most likely this is the most likely outcome. If we randomize the circles properly, this is what we might be able to obtain. So here, please take note. I mentioned about how a sample represents population, it must be random. Okay? So, and then if we do that, we are able to do that, most likely our observation is as good as the population. The statistic is as good as the population. Now, having said so, with all these 3 possible outcomes, if I take the average, 50, 33, 67, 66, so I average these 3 outcomes for the 3 times, I got 50%. And then, for your information, this is actually the estimated parameter. I hope you are able to follow me here. And these are the statistics, actually. Why is that so? Why is that not this one parameter? Because in actual reality, you will never be able to get this information. You will never, ever be able to get this information. You will never. In this case, I give you a finite population, 35, and I know how many red circles. So I got 50%. But in actual reality, you will never be able to know this information. Let's say Malaysia, hypertension. Nobody knows. Nobody knows the actual parameter. But using statistics, we can calculate the estimated parameter. So based on this one, we can compare the statistic 50 versus 50. So this is the best matching data. How about this one? 33, 50% means to say this one definitely under reported, under measurement, under observed. Okay, this one is over observation. So we measure something which is not true. So this is the most accurate because we compare to the parameter, which is this one. Okay, I hope you understand. What I'm trying to show you here, even though we do not know the actual parameter, but using statistics, provided the distribution of the outcome here distributed randomly, so they are symmetrical, they are predictable, so we are able to calculate our estimated parameter. So then the statistics, we know what they are doing. So they already calculated the actual parameter and they compare with our data, and then they can give the precision of the statistics. All right, that's how statistics works. Understand, everyone?
Yes.
Yes.
All right, so that is the first important concept. So whenever you analyze something, the computer will generate how significant your data is, how good is your estimate is. So you must automatically remember, how do the computer knows how good the estimate compared to the real value? So the computer will analyze behind at the back end, automatic, very fast, and they know what is the parameter, and then they compare your observed and then with the parameter and whether they are similar or not. That's how the computer works. That's how the statistics works. Yeah. All right. Now I go to the second premise with second fundamental relationship. I'm jumping here. Actually, for the first part, it can be one chapter of the book. This one is another. This one relationship is huge chapter of a book. It can be a 500 pages. Causality, and then I have a book here in my side by Hayes. There's a 500 again pages thickness about mediation and everything. So I will try to give this in only few slides. So relationship means that if you look at variable here, now I'm not talking about one variable. I'm talking now, you are interested to look at relationship. So relationship is always a two variable. So in this case, if you are looking at the relationship, one of the variable, we are talking about two variables. One is what we call dependent variable, where the outcome depends on something else. And then to the other end of the relationship is another variable we call independent variable. So remember, yeah, the label dependent or independent can change depending on the variable used. Example, if the dependent here I put as, let's say I put here lung cancer, and independent here, let's say the X is smoking. Smoking causing lung cancer. Y is lung cancer, X is smoking. So this is a two variable relationship. Or in statistics, we call a model that consists of two variables. Lung cancer status, yes or no. Smoking, yes or no. If they smoke, so it is more likely to get lung cancer. So the word more likely in this equation is the beta one. So the higher the beta one, the higher is the probability to get, for the smoking, to get, to cause lung cancer. All right. However, if let's say from this independent variable, which is smoking, let's say I have another bubble behind here, why a person smoke? Say mungkin more important, let's say a peer pressure, a peer influence. Peer influence, another bubble here, and then the arrow pointing to this variable. So at this particular relationship, smoking now is no longer a dependent variable. For that relationship, smoking is a dependent variable. So my point here is that the label here, the role of the variable depends on the relationship. The role, whether dependent or independent, depend on this relationship. So dependent is where the arrow is pointing at. All right. and independent is where the arrow exit. So I hope you understand that. Okay. Now I go into the causality. I'm jumping. I just want to, okay, now at the end, the last end spectrum of a relationship is what we call cause, A causing B. So one of the most fundamental statement with regard to causality is that a rooster crow does not cause the sun to rise. Ayam kokok tak semestinya matahari menyebabkan matahari terbit. Kalau ayam, kita sembelih ayam tu, for example, matahari tak terbit. You understand? So bila setiap kali ayam kokok je matahari terbit. Matahari terbit ayam kokok. So as if we try to associate the rooster's crow with the sunrise, which is coincident but not a causality. Rooster's crow does not cause. So the word cause, penyebab ni, is very strong word. So careful when we use the word causality. So if you go and read this book by Judy Pearl, for example, quite a recent book. This is a very thick book. Judy Pearl is the authority in this subject. So basically, this part of fundamental topic I'm trying to cover is about causality, A causing B. Yeah, and another important person, very dated back in 1965, is by Sir Austin Bradford Hill. So you know about Hill criteria. So he's the one who responsible to create those 9 guidelines of Hill criteria. So he mentioned a very, I like his words. He mentioned that I have no wish nor the skill to embark upon a philosophical discussion of the meaning of causation. I told you about cause, right? The cause of illness may be immediate and direct. It may be remote and indirect, underlying the observed association. But with, of course, when he gave this talk, he's talking in the occupational conference. But with the aim of occupational and almost synonymously preventive medicine in mind, so actually they're talking about preventive medicine in mind, the decisive question is whether the frequency of the desirable event of B will be influenced by the change of A. So how A affect B? All right. So basically, if you can summarize everything, it's about very simple: A causing B. So causality is about A causing B, menyebabkan B. A menyebabkan B. Teh tarik menyebabkan stroke. Contohnya, those kind of thing, those kind of statement, very strong statement. So this is the Hill criteria. I'm not going to go one by one. I hope you go back and read. Trust me, we can ask you in exam, even though I'm not going to give you in detail. We hope you will go and study every 9 of them with the example, okay? So what I'm trying to say here is that with that causality in mind, when you want to do your survey later, it's very important that you are able to visualize the relationship of those variables. We call that visualizing causality. How you can visualize causality? Just the bubble chart. You draw the bubble chart. There are many names to the bubble chart. A web of causation, conceptual framework, theoretical framework, path analysis or statistical analysis. Statistical framework. Or you can use a very formatted format or standard we call directed acyclic graph. There are many ways for you to draw your bubble chart. So basically bubble chart. So I give you an example here. When we talk about bubble chart, you must always take into consideration the role of the third variable. What is third variable? Let's say I give you an example first. So this is a simple one. A factor, so an outcome can be affected by a factor. This is a model of 2 variables. So you can have a model of 3 variables like this one, where outcome also affected by 2 multifactorial, by factor 1 and factor 2. In fact, in our actual life, everything happens multifactorial, multi-causal, not one. Or you can have the third variable. Here, this is not the third variable. This is, I'm talking about multivariate analysis. Okay. When what do I mean by third variable? So once I have this link, you can see here, this link. And so now you can see that factor 1 affecting outcome, but at the same time, factor 3 have relationship with factor 1. So somehow they are the triangle of association here, causality. This is what I call as the third factor, or dalam hubungan manusia ni, orang ketiga lah. Okay. Kalau this one, This is not, there is no orang ketiga actually. Walaupun all the three affected to the outcome, but they are all independently related to the outcome. However, when talk about this one, this factor 1 outcome factor, don't ignore this one. You can see here, this triangulation of causation here is affected, they are linked to one another, not this one. This one, these all three are not connected. So they are independent of each other. But this one, this one or this one can be the orang ketiga, can be the third variable. Or another example like this one. Even though we are talking about factor 4 here, factor 4 may be related to outcome, but through factor 2. Directly, factor 4 is not related to outcome. Or you can have another situation like this, factor 5. Factor 5 is not affecting outcome directly, or affecting factor 2, like factor 3 affecting factor 1 and outcome. No. Factor 5 is affecting the relationship. So, this is what we call confounder. This is what we call mediator. And this is what we call moderator or effect modifier. Okay, or another one we call interaction. Okay, so this is confounder. This is mediator, this is moderator, effect modifier or interaction. Ada banyak nama sini. So this is, inilah kita panggil orang ketiga. Third variable, the third variable, the third variable. My point here is that a relationship like this, a bubble chart like this one is not as simple as it is. They have roles, different roles to play. And then I'll give you one example, how to draw a good bubble chart. You will do a survey, you will do online data collection, but you have to work using online. Hopefully you will come back to campus soon. But nevertheless, I want to give you an example about one topic by Huang, smoking behavior and cessation services among male physicians in China. So the population is male physician. So they want to know whether the physician smoking behavior, because many doctors in China smoke, whether their smoking behavior affects their advice for the patient to stop smoking. Okay, if you, for example, like we believe that if you are a smoker, you are most likely not to advise your patient to stop smoking. So, but in other hand, many professionals, many doctors believe that doesn't matter. Don't follow what I do. Follow what I told you. Okay, many doctors believe like that. But now we look at certain data from analysis. So this is the bubble chart created from the study. You can see how complicated it looks, right? Okay, now follow my lead properly. So the most important, if you look at this, the title, the most important variables are smoking behavior and cessation services. So those are the two most important variables. And in this, it looks like a complicated diagram. The important variable only two, smoking and smoking cessation services. Whether the doctor just now smoked, whether it eventually prescribe smoking cessation to the patient or not. And all the other factors are the analysis, the relationship with all these two variables. So you can imagine that this is the independent variable, this is dependent variable, but they are also mediators like peer smoking. This is not really a mediator, this is a confounder actually, because you can see the arrow is pointing to the side and the arrow also pointing to the side. So this is not a mediator. Mediator is something like, do we have here mediator? I don't see any mediator here. Unfortunately, I don't see any mediation effect here. I hope you understand the difference. This is mediation. One arrow go to this side and then this one arrow go outside, right? But this one, peer smoking, from smoking to peer smoking, the arrow is not exit from smoking to peer smoking, but peer smoking is going to smoking, logically. So this is not a mediator, but this is another confounder. This is also another confounder, this is also a confounder and confounder. My point is that, oh yeah, by the way, for your information, this drawing is drawn using SEM format. SEM, you can see there's a rectangle here, and then there are also circle. So that's different connotation. Circle is something not measured directly. We call it latent variable. Example like a common knowledge. You are not able to measure common knowledge. you ask this question, 1, 2, 3, 4, 5. So these questions constitute common knowledge. So you don't measure common knowledge directly. So this is what we call as unmeasured variable, or we call it as latent variable. The one that rectangle is the one that you observe, you measured directly. So I hope you understand that one. But my point is that at the end of the day, is a smoking physician prescribed smoking cigarette service, a smoking cessation service? The answer is 0.87 odds ratio. Meaning to say that it is lower than 1. So if a doctor smoke, they are unlikely to prescribe smoking cessation service. This value, 0.87, is already adjusted for all other values. That's why this one is adjusted values, all right? Smoking, those who smoke, less likely. How less likely? 13% less likely, because 1 minus 0.87, you got 13%. So if you smoke, you are 13% less likely to prescribe smoking cessation to your patient. I hope you understand that one. I'm not going to go detail. Number 3, level of measurement. This one is the easy part. You have seen this knowledge about scale measurement has been taught since 1946. You have heard about data being nominal, ordinal, interval, and ratio. I just want to show you this slide, nothing more than just a simple fact that this is very dated knowledge. Yeah? So what I want you to understand is that for every variable that you measure, for every single variable, it can be age, it can be sex, it can be BP, it can be BMI, it can be weight, it can be height, it can be whatever. All the measurement that you observe, you must identify the level of measurement. What is the level like? So data, the data for every single variable you want to observe, it can be categorical or numerical. And if it is categorical, it can be further divided into nominal or ordinal. I'm not going to detail about this one. I hope you go back and read the difference between nominal, ordinal, interval, and ratio. So those are very critical, very important. So I hope you understand which one, for example, like between interval and ratio, which one have absolute zero, which one have not absolute zero. What do I mean by absolute zero? Temperature, for example, is zero temperature, 0 degrees Celsius. If 0 degrees Celsius means there is no temperature? No. 0 degrees Celsius does not mean that whatever object that we are holding, whatever temperature that we are having now, is no temperature. Temperature is always there. Temperature can be negative, but the 0 temperature does not mean that there is nothing. If you go to hemoglobin, if you take someone, 0 hemoglobin, meaning to say what? Very unlikely lah kan, someone to have 0 hemoglobin. Meaning to say that 0, there is no hemoglobin at all in the body, which is unlikely lah. Kan? Macam RBS, you got 0 sugar, mean that in the body there is no sugar, most likely dead people lah. But even dead people, if you take the blood, you can get some sugar. So that's what I mean. 0 in blood sugar means 0. 0 in hemoglobin means 0. 0 cholesterol means 0. But 0 temperature is not 0. Okay? Doesn't mean that you don't have any temperature. In hemoglobin, 0 hemoglobin means you do not have hemoglobin. 0 blood sugar, you don't have sugar. But 0 temperature doesn't mean that there is no temperature. Okay. Temperature is always there. Okay, so you go back and study about that one. I will not go into detail. So why is it so important for us to know all the level? Because different level have different purpose. One is qualitative, one is quantitative. What do I mean by qualitative and quantitative? Male, for example, male, female, sex, for example, male and female. That's purely qualitative. We don't quantify how male you are, how female you are. No. You want to know whether you are male or you are female. Ada yang male tetapi agak lembut-lembut. So we don't even that we don't measure how masculine you are. No, we don't measure. It's not difficult to quantify. Kalau perempuan, for example, how many are true female? There is no such thing as true or not true female. Female is female. Female, male. There is no such thing as in between. Tak ada. Walaupun in reality ada yang ketiga tu, but I'm not going to talk about that one. Dr. Samsul akan cakap benda tu. Different ways to describe, for example, like which one you can only count, which one you can calculate the proportion, or can you calculate the mean? For example, like again, male and female sex, for example, can you calculate mean of being male, mean of being female? No, cannot. If you give a label like male is 1, female is 0, so the mean should be 0 point something, but that is wrong because they are qualitative. You should not use mean. So you must know, if data is qualitative, you do not use mean, you do not use median. If data is qualitative, you can use count, you can use percentage, but you cannot use mean. But if data is numerical, whether they are interval, ratio, you can use mean and median. And then the different measurement also will determine the different statistical tests. Later, Dr. Adi will go through with that. And for your information, different level, different measurement also have different hierarchy. Different hierarchy in the sense that what you can do with the data. I mentioned just now, sex, for example, you can only count, but you cannot measure the mean. But if you look at, for example, like blood glucose, you can measure the mean of blood glucose if you want. And then the possibility of information or value from blood glucose is infinite, depending on how precise your instrument is. So that is number 3. I'm going to number 4. Number 4 here, the fundamental, the last part of the last bit is about distribution of data. So I'm jumping 4 different chapters now. The first one about representativeness, whether the sample represent parameter or not, whether the sample represent population or the statistic represent parameter or not. Number 2, I'm talking about the variable, the role of the variable. And then I'm talking about level of measurement. How will you measure those variables? And the last one, I'm talking about the distribution of data. So this is especially for data which is numerical, okay? But the count for male and female, you can do binomial distribution. That is called discrete data. But I'm talking, but as long as they are numerical, you can decide the distribution of data. Sir William Osler mentioned that medicine is the science of uncertainty and the art of probability. I want to highlight the word uncertainty and probability here. In our life, everything is not fixed. In medicine, everything is not fixed. Not fixed. You already in year 4, you have gone through many clinical wards before, exercise before. You have seen that one antibiotic may be good for one patient for the same disease, but it may not good for the different patient with the same disease. No. So there's no one size fit all in medicine. Medicine is about uncertainty and about probability. So what we want to do is the most probable things of our life, but be wary that be prepared that whatever we do, we may not get the actual replica or the actual outcome. And when we talk about shape of data, basically any data that we have, we can set and we can align them, and then we can look at the distribution like. And this distribution is meant for numerical value, regardless whether discrete or continuous. So these are examples of some distribution. I'm not going to detail here. There are, if discrete, you can have binomial, Poisson, negative binomial, hypergeometry, multinomial, blah, blah, blah. Continuous, most commonly, is normal distribution, T distribution, chi-square distribution, F distribution. But for your level, I want you to really understand about normal or not normal, okay? For you, I want you to study about normal or not normal. And it's going to be very simple. What is normal distribution like? It is a bell-shaped curve. It is a symmetrical curve. And it contains one mode. I mean, one peak here, all right? So this is an example of bell-shaped curve, a normal curve. Normal curve is like this. It's like the line here. So even if you can, for example, create the histogram, but more importantly is that for you to know the curve. Later you can ask Dr. Adil how to examine normal curve in your data. So why I ask you to focus only in normal distribution? Because normal distribution is what most of the biological and psychological variables distributed like. For example, like our weight. So let's say for female, the formulation, for example, majority of, let's say, it depends on age as well, and then whether you are married or not married. You have not married, normally slim, lepas married semua kembang. So those kind of things. So let's say ambil regular, non-merit or students, maybe you start dengan 50 something for female. So of course there are some female who are 100 kilos and there are also some female which is a 40 kilos weight. So they are extreme of two ends, but majority are in the middle, which is that's what we call as normal distribution. And if you plot this probability density function into a cumulative distribution function, you will get a S-curve like this one, okay? Whereby this one in the middle here is the highest slope that represent the peak here. So there's a very statistics. You must know differential. This is differential. If you differentiate this one, you got this one. You integrate this one, you got this one. Pengkamilan dengan perbedaan, remember? So this is the histogram that you draw. And another reason why we use normal distribution is because of the predictive model. Many predictive model assume that it is a normal distribution. Kalau you normal distribution, then you can do a lot of normality. So into practical part of it, how to check for normal distribution since you are using R nowadays. So I changed my slide a bit. So basically there are two ways for you to check whether your distribution is normal or not. Whether you use descriptively by looking at it, or you use certain specific tests like test of normality. If you ask me which one I prefer, number one, not number two. Number two is very specific, yes, but they have many flaws. There are many caveats. So I prefer number one, and then there are many other things, but I list only two. You are using histogram, this normal curve, and QQ plot. So what is a normal curve? Normal curve, something like this one. You can see this is the histogram, and then you plot the normal curve on it. So then you decide. So you can see here, it is not really symmetrical, right? You can see the tail is slightly higher, longer on the right side. So they are somehow skewed a bit to the right. So skewed to the right. Ekor dia panjang kat belah sini. So they are not really symmetrical. So you decide, this is normal for you or not normal for you? Okay, you decide. If you ask me, I prefer to be biased or normal. I like my data to be normal because easy for me to analyze, and the analysis used is more robust. You can see this is I wish you good luck when you learn R later. This is the thing that you have to key in to get this curve. Or you can use QQ plot. I told you here, histogram with normal curve and QQ plot. So there are many ways to do QQ plot. Using the basic R package, you can get this curve very easy. So G is my data here. I'm using at H variable in my data. So I call it G. So, and then I use a norm, QQ norm. So I got the dotted, all these dots. And I add in another command, QQ line, I got this line. So how to interpret this finding? If majority of my observation here, this one bubble here, lay on top of the line, we call it as normal curve. So looking at this one is very descriptive. Yeah, there are many observations on the dot, on the line here, but many also outside. So again, you have to decide. You can see here, this is the long tail here corresponding to the Y data is not fitting well here. Or if you don't want to use, you want to use more advanced like QQ plot. So this is the example of QQ plot. This is a QQ plot in R. You can get even 95 confidence interval. So those that outside this value 95%. So those are the one that you feel that they are outlier. So if you believe this is substantial, they're significant, you can call this one as not significant. Or the third way, or the second way to measure is using the normality. You can see there are many tests for normality here. In SPSS, you only have two, corrected Kolmogorov-Smirnov test and Shapiro-Wilk test. In R, you can have everything that you like. Example I'm giving here is Shapiro-Wilk normality test in R. So from the analysis, you can get the p-value is significant. When the p-value is significant means H is not normal. Okay, so this is based on test of normality. Why I said I prefer this one, then this one. Why? Because if you use normality tests like Shapiro-Wilk, like Anderson-Darling, like Jack-Bera test, small sample almost always pass a normality test. But large sample, a minor deviation can flag the data to be not normal. So they are very sensitive. normality tests like this one are very sensitive depending on the sample size. All right, that's why I prefer this one. When I was in London and UK, I did my training. We never use this test. We always use eyeballing. Look at data and whether it's normal or not normal. And yes, eyeballing you can use. And why is it important to determine normal or not normal? What to do if data is not normal? First, you have to validate your data entry, whether, let's say, for example, age is 20 years old, you enter 200 years old, for example. So you have to validate your data entry. You have to check again whether you entered correctly or not. If data remain the same, what you can do is transform the data. I cannot give some example how I transform the data and change data from not normal to become normal. And by the way, guys, data is normal or not normal. Jangan cakap abnormal, ya. This is not hypertension. Normal or not normal. So this is the correct term to use. Not abnormal data, no. Normal or not normal distribution of data. So normal is noun. So if data is not normal, you transform the data. And finally, if you don't want to transform the data is correctly entered and you don't want to transform, you can use non-parametric tests. Later you will learn from Dr. Adil, parametric something like t-test. Non-parametric like Mann-Whitney U test is a non-parametric test. So because you don't want data is not normal, you don't want to transform, you use a non-parametric test, a test that consider data to be not normal. Okay, so come to my last 3 slides. Okay, the practical part of it. I have another 15-minute video. No, 10-minute video. So far, any question? Right? In presenter view. Kenapa tak beritahu tadi? Oh, everybody see presenter, not the full text, ya?
Presenter, Prof.
La ilaha illallah. Kenapa dia tak beritahu?
Kita ingat Prof saja je pasang.
Okey. Sekarang nampak dah?
Nampak.
Kenapa lah tak beritahu awal? Saya tak pasang yang teks. Okay, fine. So the statistical analysis. So I mentioned just now, earlier part, that the earlier part is that I mentioned when we do analysis from my first slide, I mentioned that there are 2 types of analysis, descriptive, analytical. And I told you guys that descriptive means 1 variable, right?
Yes.
Analytical means more than 1. All right, descriptive, how, later when you see Dr. Adil after this, how to describe a data. So when descriptive, univariable, 1 variable. So you have whether it is blue or red, both are V. V means variable, regardless. There is no role here. All right, but when you look at when you want to look at the relationship, so you will start seeing the arrow there, right? You start seeing the arrow there, so you can see that now one have to assume dependent role, and the other variable here will assume the independent role. So here in this descriptive, you are not interested to look at the relationship. There's no arrow here. Both are just a variable. So when you want to analyze V, regardless the red one or the blue one, you will analyze separately. You are not interested to look at the relationship. We call this descriptive statistics. So descriptive is very much important for to measure the workload, the burden, the magnitude of illness. But by variable analysis, when you talk about analytical statistics, the word compare comes in. You want to look at whether one variable affects the other variable. All right, that's the concept of it. Of course, multivariate when you have more than 2 variables. So actually, this one also multi, but we use a very specific tool. We call it bivariable because the statistic-wise is different. And then example like univariate, you want to describe age. So this one can become age. This one can become hypertension. But regardless whether they are dependent or independent, at this juncture, we are not interested to look at the association. We can describe age, we can describe sex, we can describe hypertension. But we are not interested to look at the association. However, once we are interested to study the association, so the word compare comes in. You see? For example, like this one can be sex. This one can be hypertension. So you want to know who have the higher proportion of hypertension, male or female. All right. So you can say that if you can see that the proportion of hypertension higher among male, so you would say that male have higher risk to have hypertension. All right. So you attribute the sex to the risk or to the distribution of hypertension. So that's what we call as relationship. Obviously, multivariate is a more advanced, of which we are not going to teach you that. My last, is it my last slide? My third slide. Okay. So again, I mentioned about this one, descriptive versus analytical. Descriptive means a single variable. Our interest in magnitude or burden of disease. Normally from descriptive, we can generate hypothesis. However, in analytical, normally involve multiple variable. We try to compare conditions. We test hypothesis. And of course, we study relationship or causality. So how to describe a data? So I give you my second last slide. How to describe a data? The purpose is to describe a data. First, check the level of measurement. You see? Now I am now using all the fundamental just now. Level of measurement, numerical or categorical. If it is numerical, check normality, normal or not normal. If they are normal, you describe using mean. If not normal, you describe using median. Example, let's say you have age. Age is numerical or categorical. It can be both, right? But how would you measure? How do you want to analyze? Let's say I want to analyze age as numerical. So I must check the normality. Remember, I told you how to check normality, two methods, descriptive or the test. Descriptive, there are two ways I mentioned. One is the histogram and the curve. Another one is the QQ plot. Remember? And the test, there are many tests. Example I gave is Shapiro-Wilk test. From the test, I said that the age is normal. So what I will be using is that I will describe the mean age and the standard deviation of the age. However, based on my normality check, I discovered that age is not normal. So I have to measure the median of the age and interquartile range of the age. I cannot use any mean. I cannot use standard deviation or any product of mean. This one you have learned in year one. So we might ask a simple question like, in short note, describe 5 differences of mean and median. Example lah. So you must know when to use mean, when to use median. Now, if age just now I categorize children, young adult, elderly. Example, 3 categories. So now obviously they are categorical. For categorical data, you do not need to check for normality. Very easy for categorical. Straight away you use count and percentage. Hidup senang. Kalau data categorical, hidup senang. Tak payah check normality. Tetapi for your information, if you categorize certain information, you may lose certain information as well, certain values. So you may not be able to get a cut-off point when the person is high risk to get hypertension, blah blah blah. So you might lose certain valuable information. So, but then if your data is categorical, it's easier to describe. All right. And when I talk about analytical statistics, analytical means you want to detect the presence, detect differences or detect the presence of differences, trying to measure the magnitude of differences. One, if you see one bar, for example, one is high, one is low. So one, you know that when there are difference. But if you want to measure how big is the difference, that is number 2. Measure the magnitude of difference. Now, if you have enough information, one bar and then another bar slightly higher, the third bar is even higher. So what you see is pattern. So you can see there is a pattern. The prevalence is higher and higher over the years. So if you have the pattern, the last step you can do is prediction. So if the prevalence is keep on increasing, example like COVID-19, you see that the case is going up, going up, going up, going up. So the next week, the thing can go up depending on the variable that you use. So when we say compare data, we can say that we can compare the means, the variance, or you can compare the proportions, or you can compare the regression, okay, like this one. So I just give some example. I think that's all from me. So this one, this is just example. When I said compare means, you can see here, these are two numerical distribution here. You compare the mean, the tip here. So obviously number 2 is higher than number 1. If you convert data into proportion, percentage, 2 again is higher than 1. If you have two regression line, number 1 and number 2, you can see that 1 is higher slope. So every changes of x will change a lot in the y in 1 compared the y in 2. So I hope you understand what I'm trying to talking. This is very advanced. Number 3 is very advanced. It's multivariate analysis. You are not going to go through all those things. But these two, compare means and compare proportions, you will go through, inshallah. So I justified the word proportion here in chi-square, but I'm not going into detail about all those things. I think that's all from me, unless you have any questions. Anyone? Anyone? Tak ada. Sama je kalau online tak online, semua diam . Okay, tak ada . So tak ada. I believe Dr. Adil already gave you the YouTube channel, I believe, where he go through all those R Studio with you, R and R Studio. I hope you can install, or if not, you have to use the R Studio in cloud. I wish you all the best. Using R is very steep, but we cannot use SPSS, because if you use SPSS, you have to install SPSS, and SPSS is not free. So very difficult for everyone to install SPSS, and R is very light, very easy. Everybody can install R in their any computer. I think with that, there is no more question. I thank everyone, inshallah. So hope everyone is good, learning okay, inshallah. If anything, let us know. I think with that, I thank you. Assalamualaikum.
Thank you, bro.
Thank you, bro.
Thank you, bro.
Thank you.
Okay, bye.
Thank you.